Right. This is a test for satellite motion and astronomy review. Now, what I'm going to do is, I have two forms, A and B. You may have A or you may have B, depending on the seating arrangement. This will take place in the planetarium. Some of you were confused about that I saw today. Today is the day before the test. So if you watch this or listen to this review, make sure you go directly to the planetarium, and I will see you tomorrow at it's day one, so it'll be block 3 in the planetarium. So that's going to be from 11:10 to 12:40 in the planetarium. We're going to take the test, and we will also finish the movie. Okay. Now, so I'm going to look at Form A. Now, Form A goes right by the book. So the order in which I'm going to review this, I'm using Form A to review, and it's going to go directly from the book. Okay, now, and it's a very standard test. It's all conceptual. You know, make sure you have a good outline, and you should be fine. All right. So you're going to have to know things like, the orbital speed of the Earth. You know that we're moving 8,000 meters per second. It's really quite amazing. That's how fast we're going. That's our orbital speed. It's really quite amazing. You're going to have to know things like, where do we put satellites? Above what distance and why? Well, you have to get it above the atmosphere, because otherwise, the atmosphere will act as a drag on the satellites, and the orbit will degrade. The orbit of the satellite. Describe the orbit. Is it a constant orbit? Is the speed constant or not? You've got to know what an ellipse is. What's the relationship between an ellipse and a circle? What's a period? So, for instance, okay, let's talk about period. Let's say we have a frequency of a wave. Let's say we have ocean waves, and the frequency of the ocean waves is 20 waves in 1 hour. 20 waves in 1 hour. So the frequency would be 20 waves per hour. Okay, that's the frequency. What's the frequency? 20 waves in 1 hour. So, but what is the time? What's the time? What's the period of one wave? What's the period? What's the wave period? Well, if it's 20 waves in 1 hour, in 1 hour, it would be how many waves? The time per wave. In other words, how long is it for a wave? What's the period of the wave? So the period of the wave is the inverse of the frequency. So, in other words, what's the period? If I have a satellite doing, 20 revolutions in a day. Let's say 24 revolutions in a day, right? 24 revolutions in 24 hours in one day. So what would be the period? The period would be 1 hour. So in other words, what's the length of a revolution? If it's 24 revolutions in one day, what's the period? So the period, in other words, what's the length of time for one revolution? That's the period. So you've got to know what a period is. Now, what about the relationship between the period, in other words, how fast it's going, how long it takes for one revolution, and the height of the satellite. The height of the satellite. Okay, so it's going to be 150 kilometers is going to have a certain period. Okay, how long will it be? Maybe let's say it's going to be a period of uh, 1 hour. If I move that out farther, isn't it going to be going a farther distance? Okay, so what's going to happen to its speed? You know, remember Kepler. Remember what he said when and we did it with the basketball and the balls, where as the planet got closer to the sun, what happened to the speed of it? Okay, so higher orbits, higher satellites, do they move at a greater speed or a less speed? All right, let's see what else we got. Let's see. So, what's the fastest moving planet in our solar system? I think we did that in the planetarium. Remember, planets are satellites. You know, how many satellites does the sun have? Well, it has essentially, 9 satellites. Unless you demote Pluto, of course. But it has Mercury, Venus, Earth, third rock from the sun. You have Mars, Jupiter, Saturn, etc. So those are satellites of the sun. Now, let's say I put an object halfway between the Earth and the Moon. Is it going to fall towards the Earth, or is it going to fall towards the Moon? Well, it would have to be awfully close to the Moon for it to fall to the Moon, because the Earth is massive compared to the Moon. So if it's halfway, it's going to fall towards a larger object, which is the Earth. That's a pretty easy one. What's the escape velocity? You have to know the escape velocity of the Earth, of a satellite or of a rocket when it's going to escape the Earth's clutches. What is that escape velocity? For instance, if I take, if I launched a rocket at 10 kilometers per second, what will happen? Or 8 kilometers per second, what's going to happen? What's going to happen? So what's that velocity? And what does it mean? Escape velocity. What does that mean? Listen to how I phrase this. The escape velocity of from Earth is x kilometers per second. Okay. If I maintain a velocity of 8 kilometers per second or 7 kilometers per second away from the Earth, what will happen? Will it escape? So, you got to look at the way the question is worded. Let's say I have a satellite, and it stays above Abu Dhabi. The Earth rotates. The Earth revolves on its axis, rotates on its axis, and the satellite stays above Abu Dhabi, right? So what's the orbital period of the satellite? What's the orbital period of the satellite? Do you know what it's called, by the way, when something stays stationary above a point on the Earth? All right, let's say the satellite was the Moon. Let's say the satellite's the Moon. Earth has a satellite, it's the Moon. What's the period of the Moon? Now, we know that, what's constant for a circular orbit? What's constant for a circular orbit? Okay, what's constant? Okay, is the speed constant? Now, if the speed is constant for a circular orbit, it's certainly not constant for an elliptical orbit. But what is constant for an elliptical orbit? Do you know? Do you remember? We talked about this. What is constant for an elliptical orbit? Now, what's the, what's the force of gravity? What's the force of gravity that does work on a satellite when it's in an elliptical orbit, a circular orbit, or both? Okay, and that has something to do with, what's constant. Okay, that has to do something with what's constant. So let me ask you something again. If I have two orbits, okay, let's say one is 150 kilometers. What's going to be the period of that satellite versus the period of a satellite that's 600 kilometers? Or let's say it's at the moon. The closer the satellite, now we're talking about a circular orbit, a circular orbital satellite. What's going to have a longer period? The satellite that's close to the Earth orbiting, or the satellite that's far from the Earth? All right. You need to know the escape velocity, simple number. And where does a satellite, let's say a circular orbit satellite, where do you have the greatest kinetic energy? Where do you have the greatest kinetic energy? If it's circular. Okay? It's that's a trick question if you get it wrong. All right, now this is something I was trying to say before, or maybe I deleted that part. Let's say you have a tangent line, right? Let's say you have a tangent line. You know what a tangent line is? A tangent of a circle is where you have a line and one point of the circle is common. Okay. So let's say you have a tangent line. Right now, it's right on the ground. It's not up in space. It's right on the ground. So you're walking, right? Right. Let's say it's 8,000 meters, and that's tangent. It's not going along the curve of the Earth. You're walking, right? So obviously you're going to have a curvature of the Earth, right? An average curvature. Let's say the Earth is a ball. Let's say it's round, perfectly round, and it's not, but let's say that. So you have this tangent line, and you're walking. Let's call that the x-axis. And how much of a drop-off are you going to get every, let's say, 8,000 meters? What's the slope? Rise over run. Okay. For every 8,000 meters, how much are you going to drop off? 8,000 meters. And 8,000 meters isn't that far. It's a few miles, but it's not that far. So let's say your tangent line was 8,000 miles. Right, and the line is right on the ground. Picture this line that goes right on the ground and goes straight. Obviously, with the curve of the Earth, it's not going to be perfectly. There's going to be a drop off because the Earth is curved, and this line is straight. I'm talking about a tangent line. Okay, enough said. All right, let me put it on pause. All right. Now, let's talk about the orbital speed of the Earth is about 8,000 meters per second or 8 kilometers per second. We know that, right? That's easy. And let's say what would be the minimal orbital speed about the Moon? What would that be? Would it be greater or less than 8 kilometers per second? What would it be? And if I could throw a baseball, let's say, here's a question. This is the ultimate question. Let's say you could throw a baseball horizontally, right, at a speed of 8 kilometers per second, and let's say There is no air drag and nothing to stop it. You're throwing it horizontally. What would happen? What would happen? And now let me ask you this, okay? Let me ask you this. So the space shuttle, if it's orbiting the Earth, what's the space shuttle? It's simply what? Okay? And if I throw that baseball, what is it? What is it? And what's going to happen to it? All right? Put on pause just for a second. All right. The last two things I want to leave you with. A, I want to know the relationship between potential and kinetic energy for a satellite orbiting the Earth, and I want you to be able to describe how a circular and elliptical satellite orbit, how they vary, a circular and an elliptical. All right, that's it. All right, it's actually a pretty good, if you take me seriously and you do a little studying using this as a guide, you're going to score some serious points. But only if you're using this as a guide, not a template. Okay? Yes? So you have to actually read. And I saw some people, some of you were upset. I just gave everybody credit for the homework, but I'll tell you, if I saw some of the outlines. Some of the outlines are good, and you're going to do well based on if you use your outline versus what I just went over. If you can answer every question, if you can challenge everything I say with your outline, you're going to be fine. Okay? And I haven't decided whether or not it's in pairs, so don't even go there. Make sure you're ready for an individual test. And even if it is pairs, if you're absent, I don't know what else to do. If you're absent, you have to take it individually. That's the rule. Okay, understood? So we haven't had a lot of class time since the last test, so it's a little weird. So, but good luck and get some sleep tonight. Right? Come in well rested tomorrow, and I'll meet you in the planetarium. Goodbye.